In this last video, we are going to talk about how we can use tangents of a circle. The first is verifying that a segment or a line is in fact tangent to a circle. And in order to do that, we are going to use the converse of the Pythagorean theorem. Remember, the converse of the Pythagorean theorem proves that a triangle is a right triangle is acute, or a triangle is obtuse. In this one, we want to prove that a squared plus b squared does in fact equal c squared, and that would be enough to prove that EF is a tangent. Now, remember that the radius and a tangent will intersect at the point of tangency and create a 90-degree angle when that line is in fact tangent. So this becomes our right angle here. This highlighted segment here is our hypotenuse. That's the longest side. And now we just want to math it out to verify that, oh yeah, look, 3,721 does equal itself. Therefore, segment EF is tangent to the circle. Now, this next question says, tell whether segment AB is tangent to circle C. So what's helpful, I think, is to identify that hypotenuse. So in this situation, it would be, or that longest side would be segment CB. This is where my right angle would exist if this line was in fact tangent. And now my Pythagorean theorem would look like 5 squared plus 14 squared. Does it equal 15 squared? That's the question we want to know. And over here, we can see that, oh, the left side does not equal the right side. Therefore, segment AB is not tangent to circle C. Even though it looks like it's tangent to the circle, it's not. In these next two examples, we are going to use the Pythagorean theorem to find the value of a variable. So this means that our segments that were given outside of the circle are in fact tangent. So because they're tangent to the circle already, we can use the Pythagorean theorem, which means that this angle right here is a right angle. And it also means that this angle over here is a right angle. So again, let's identify what our hypotenuse would be for each triangle. In this one, it would be segment LK. In this one, it would also be segment LK. And notice that we're not always solving for the hypotenuse itself. Sometimes we're solving for the hypotenuse, but sometimes we're solving for one of the legs of the right triangle. So I'll give you a little bit to tackle those two questions. And if you use the Pythagorean theorem, you should end up with x equals 20.2 for the first one and x equals 11.4 for the second one. All right, this next question is a challenge question. We still know that segment JK is tangent to the circle. However, this x right here is not asking for, it's not representing the whole segment KL. It's only representing this part right here. So we have to remember that all radii are equal in a circle. So if the distance from L to this point J is 10, then that means the distance from L to this point on the circle is also 10, which means that this segment is represented by the expression x plus 10. So now when we go to perform the Pythagorean theorem, we have 10 squared plus 24 squared equals the quantity x plus 10 squared. This requires a little bit of additional math. We have to actually multiply this out. Then we have to subtract these to get a 0 on one side, so we can actually use the quadratic formula, or we can factor in order to solve. So I will leave that one as a challenge question for you, and you can find the answers to that on the classroom. The next thing that we can do with tangents is that if two tangents share a common external point, so here we have this point on the exterior A. Notice how AB is tangent to the circle and that AD is tangent to the same circle. Well, what happens is that means that these two segments, segment AB and segment AD, are congruent to each other, meaning they have the same length. So 6x minus 3 is the same as 5x plus 7. And that allows us to create this equation over here that we can use to then solve for x. 6x minus 3 equals 5x plus 7. And we can solve that for x. And we end up with x equals 10. So again, if two segments are coming from the same exterior point and are tangent to the same circle, then these segments have to be equal to each other. So on the next page, you'll just find a couple more examples using the fact that they have a common point on the exterior. So here is my exterior point. Segment BA is going to be congruent to segment BC, which then allows me to create an equation. In order to solve for x. Now, once I find the value of x, I can always substitute it back into one of the expressions to find the length of each of those segments. And that's what it asks you to do in example G. In example G, you want to find the value of x, but then you also want to take that value of x and substitute it into the expression to find the length of segment AB. The last topic that we're going to talk about with respect to tangents is common tangents. So here, a common tangent is a line or a segment that is tangent to two coplanar circles. So that means that you have two circles that are in the same plane, and there is a tangent that is shared between those two circles. We can have a common internal tangent. So if you take a look at letter A, this represents what common internal tangents will look like. They intersect the segment that connects the centers of the two circles. So segment CD is the segment that connects the center of circle C and the center of circle D. Line K and line J intersect. So these would be common internal tangents. And then letter B is an example of two common external tangents. They do not intersect segment AB. So these would be common external. Now, just another couple examples. What if I have these two circles right here? Couldn't I draw a common external tangent there? And then could I draw another common external tangent here? And then could I draw a common internal tangent right here? I think so, because if this is the segment that connects the two centers together, then that would be a common internal tangent. So see how you can have a mixture between common internal and external in the same diagram. This figure would have a total of 3 common tangents. And that's it for tangents. Have a great day. See ya.